single painting, a small number of paintings. But we're also working on problems of what's called stylometry, the mathematical description of an artist's style. And the work quite a bit on Piet Mondrian, the neoplastic abstractionist painter who worked in the Netherlands and the United States. You're all familiar with his works. It consists of horizontal and vertical black lines and red, yellow, blue, and black. No natural colors, no green. You want to be artificial and so forth. And we have a computer method that will take one of his paintings and describe it by where the positions of the horizontal and vertical lines are, and the colors and so forth. It's an abstraction. It's not an accurate representation. You don't want to look at this in the museum, but it's it allows us to now look. We did it for I think 70 of his paintings, and we used a technique called machine learning to try to learn the style of Mondrian. And what we needed were some paintings that were like Mondrian, but not quite, but were not Mondrian. We needed near misses, as we said. And so we used X-ray images of several of his paintings, the transatlantic paintings, where he would put down a line, I don't know this one, but maybe a line here, and then he would sit there for a couple of days and say, no, I don't like it there, I'm going to put it here. But we can see in X-rays that he liked it here for a while, but it's not a true Mondrian. He went over it. And so we have examples of true Mondrians, the ones we see, and the near misses. And we trained a computer to be able to recognize and, in fact, to generate new fake Mondrians. And I don't have time to go through all of that, but I just wanted to say we are now looking at whole corpora to try and abstract out, style. And in this case, it's a very sort of rarefied style, figures or things like that. And the last painting I have time to talk about this evening is an incredible masterpiece by Jan van Eyck, portrait of Arnolfini and his wife. We're now back to the Hockney claim. Hockney believes this painting was executed using some sort of optical projection. Well, if this was executed under projections, we can answer the question, what focal length projector would have been used? So all of you who are photographers are familiar with the following phenomenon. Here's a photograph of me many years ago as a beginning assistant professor at Swarthmore College, taken with a standard 50mm camera with a short focal length or wide angle lens. Notice the size of me and the size of those pillars. Then the photographer put on a 50mm lens, a normal lens, which magnifies everything by a factor of 2. But he stood back from me twice as far so as to ensure that my size in this picture is the same as over here, okay? But look at the pillars. The pillars appear larger. Then he put on a telephoto lens, 200mm, a factor of 4, and stepped back from me 4 times as far as from here to ensure I'm the same size. And now look at the pillars. These are all in perfect perspective. And they're photographs after all. But it's just the center of projection, or as we say in computer vision, the camera model. How far away you are. Well, it's simple optics. In fact, I teach my undergraduate art history majors how to do it. That if you know the sizes of the objects and their relative placements, and you have a photograph or an accurate tracing, you can work backwards and infer what focal length was used for that tracing or photograph. Well, so I'm the same size and the color is different. So we had to make a computer graphics model of the tableau. And here is that tableau from the side, and here's the painting to scale in this tableau virtual. The image is going to be upside down. Now I'll illustrate it with a lens, but the mathematics is just the same as if we use a concave mirror. And you ask, where would I put the screen, the film, if you will, and where would I put the lens such that the sizes of the images in the projection correspond to the size of the real object. But these aren't real objects, but you get the idea. If you put the lens here, then the size of the image of the chandelier corresponds to the size of the real chandelier. Size of Arnolfini corresponds to Arnolfini factor for 13 objects in this entire tableau. If you try and put the lens anywhere else, you might get a couple right, but you won't get them all right. This is the best mean squared error fit. And once you have this set up, you have the object distance, this is from the object to the lens, And the image distance, this is from the image to lens, anyone in physics can calculate the focal length from that using lens equation, and it turns out to be about 61 plus or minus 8 centimeters. Well, Hockney and his colleague Charles Falco made the following claim. Van Eyck placed a convex mirror at the very center of this Arnolfini masterpiece. The very mirror which, turned around, he may well have used to construct the image. So here's a close-up, a detail of that mirror. It's perhaps the most famous mirror in all of art. It's only a couple centimeters high. You see the back of Arnolfini, you see the back of his wife, you see the two witnesses to the wedding coming through the doorway. And it's clearly a convex mirror. You can see by the distortion in the window and in the bed and so forth. Well, to estimate its focal length, we have to estimate its radius of curvature. The New York Times got it completely wrong when they were talking about my work. It's not the radius of the mirror, it's the radius of curvature of the mirror. The difference between the belly of a woman 1 month pregnant and 9 months pregnant. And here's how we did it. We've done it several ways. This one was just published last month. Here is a photograph of a convex mirror on the ceiling in a research lab in Japan, actually. And lines that we know are straight in the real world appear curved. So our method says, if we know this line should be straight, straighten it. And that allows us to deform the entire image to straighten those straight lines, and we get something like this. I know it looks weird, but all those lines are now straight. And one of the benefits of our method is that it then allows us to infer the actual shape of the mirror. Was it a section of a sphere, a paraboloid, and so forth, and to do that. So we applied this technique to the image in the Arnolfini painting portrait. And here's the image we got. So look at the window, much more rectilinear. It's much more rectilinear all the way throughout here. If you do perspective analysis, it's much more coherent than the window. I find this an absolutely amazing image. This is the view you would get if you were to walk into Arnolfini's room, stand at that mirror, turn around, and look back into his tableau, revealed for the first time 600 years after this painting was made. And the reason we did it was to calculate that radius of curvature and then the focal length. And so here's what I've just shown you. And here's that mirror on the back wall. And if Hockney's right, then the focal length of this should be pretty close to 61 plus or minus 8 centimeters. When you go through the math, the focal length turns out to be about 18 plus or minus 4 centimeters. Much too short to have been used as a claim. Here's from my Scientific American article a way of illustrating it. So here's the putative projection mirror. The radius of curvature is this distance. The focal length is 61 centimeters. It turns out to be half that distance. And here it is for the back mirror. Simply, positively could not have been used. There are a number of other reasons that we know for sure it could not have been used. Experts in optics at that time know that they put pitch in the back. They would blow big spheres of glass, put pitch in, or put silver and other metals in, and then seal it with black pitch, and then cut it, break it and cut it, so the backside wouldn't have been reflective whatsoever. Moreover, it's hand blown, so it's not going to be a nice shape, so that the image it projects is going to be blurry, not distorted, but blurry. And even if it had been perfectly shaped, the blur spot, the sharpest image you could possibly get, turns out to be about 1.5 centimeters across, much too blurry to get. So there's no question it could not have been used. But what about, okay, so if that mirror couldn't have been used, maybe another mirror. Well, is that possible? And the answer is no. Why? Because under any projection, the perspective should be coherent within any sort of putative exposure area. So if you look at the perspective lines on the floor, these two lines meet here, but this one doesn't meet at all. It's way off. Or these two lines, which are parallel in the room, clearly, should meet at a vanishing point, but they don't, and so forth. It's a perspectival mess. Now, that doesn't mean it's a bad painting whatsoever. I'm not making an aesthetic judgment. All I'm saying is that it does not cohere with the rules of geometrical perspective. Well, what about that chandelier? David Hockney got on CBS 60 Minutes and told 8 million people, quote, that chandelier is in perfect perspective, end quote. And then he says, oh, well, that is evidence that was done under optical projections. I thought I'd check. Here is the 6-arm chandelier. We're looking straight down on top of it. Number of the arms, 1, 2, 3, 4, 5, 6. Consider 2 points like those decorative crockets hanging on the arms, those define a line in Arnolfini's roof. That line is parallel to the floor. Think of my two arms as chandelier arms. Think of this elbow and this elbow as defining a line. That line is parallel to the floor because these are at the same elevation. And that line is perpendicular to the vertical plane bisecting these two arms, okay? Think of two other points, like my thumbs. Those define a line in this room. That line is parallel to the floor because these are at the same elevation, and perpendicular to the vertical plane bisecting these two arms. So those two lines are parallel in Arnolfini's roof, okay? Likewise for all of these, all right? Here's what I just showed you. And if you think about symmetry, you'll realize that these lines are also parallel. And if you really think about it, the lines defined by corresponding points on arms 2 and 5 are also parallel. All of these lines are parallel in Arnolfini's roof. So here's a symmetric computer graphics model, and, which is a projection, if we take these lines and extend them, i.e. make a projection, they should meet at a vanishing point. So we take a line from here through here and extend it, here through here and extend it. They better meet at a vanishing point. And bingo, they do, of course. It's computer graphics. Here's the Arnolfini chandelier. Hockney has looked at this for a very long time, and he believes it's, quote, in perfect perspective. So if we do the same kind of analysis on this chandelier, we better get a good vanishing point down here if Hockney's right. When you do it, here's what you get. Kaboom. It's a mess. Absolute positive mess, not even close to being in proper perspective. No hint of a vanishing point down here. No, not at all. Here is just a sort of close-up to show you how I did that. Lines like this, and 15 such lines. No hint of a vanishing point down here. So after I published this in Scientific American, Hockney and his colleagues said, well, maybe it's in perfect perspective. It's just that the arms were really goofy, really poorly made, that the artisans hand soldered the crockets haphazardly along it. But it's really in perfect perspective, but it's just the arms better. Well, you go to experts in denandry, the decorative metalwork of the early Renaissance, and they say, no, these would have been very symmetric because these arms would have been made from the same mold. You make 6 identical arms and then array them around the central staff. I and Antonio Crunisi have done photographic studies of the same sort of photographs of these kinds of chandeliers and find in museum collections, especially in Bruges and Brussels, and we find they're very symmetric to about 1 millimeter, not 10 centimeters. And then I've gone to museum collections and actually measured them with a tape measure. They're all symmetric to about 1 millimeter, not a whopping 10 centimeters off. So this is how far off they would be, have to be consistent with Hockney. Much too large, and hence would have been